Right, it's a Mei M2 question, June 2010, question 4 on work and energy and friction. This is the first part of the question. Pause the video and just take a moment to read this. Then we carry on to the second part of the question here. Well, that's the main part of the question. So doing this stage by stage, let's start working through the first bit. For this bit, we've got to show that mu is about 0.25. That's where we're going for this part at the bottom. We know that P is 58 and it's on the point of slipping, it says. So let's just draw friction on here like this. And we know if it's on the point of slipping that this frictional force is mu R, where this is R, the reaction, slightly crooked, that's R, and this is the weight, 16G. Right, for this question then, we need to form some equations, the usual equations. First of all, we know that P is 58 because we've just told us. Resolving vertically, we've got 58 sine 35 plus 16G equals R. Right, because I put P in as 58. Resolving horizontally, P cos 35, 58 cos 35 equals mu times R. Well, there's your two equations, and hopefully you can see what we've got to do. Pause the video and just have a think for a minute. We want to find mu from that. So, okay, putting them together, 58 cos 35 equals mu times 58 sine 35 plus 16G. On your calculator, then work out 58 cos 35 divided by the bracket on the right here, and we get mu equals 0.24997 I've got, which means mu as required is approximately 0.25. Right, that's the first part of the question done, and there was 5 marks for that part of the question. There was a method mark for resolving vertically and a method mark for resolving horizontally, an accuracy mark for it as well, and likewise for that. So 5 questions, 5 marks. I mean, that's 1, 2, 3, 4. Presumably an accuracy mark at the end. Yeah, that's right. 1, 2, 3, 4, 5. That's that part done. Carrying on then. The applied force has suddenly increased to P equals 70, and the box moves against friction. Okay, so we've got we take mu to be 0.25. Okay. So the box reaches a speed of 1.5 meters per second from rest after 5 seconds. Let's just jot that down first of all. U equals 0, V equals 1.5, T equals 5, and the distance moved is 3 meters. Let's go through this stage by stage. For the first part, the work done by the applied force of 70 newtons. Right, well, that's straightforward. The work done, just to remind you of how it looks here. The force of 70 is at an angle of 35 degrees. Right? So there's 70 here, and that's 35 degrees angle there. It moves against friction and another horizontal retarding force. I'll call that S. and friction. Okay, the work done by the applied force of 70 will be, by definition of the work done by force, F cos theta times d. So it's 70 cos 35, the component of force in the direction of motion, times the distance it's moved, which is 3. And that comes to be 172 joules. And the power developed, the average power, and the definition of power is rate of working. So the average power being developed by this force is the work done over the time taken. 172 then divided by 5 seconds, and that comes to 34.4 watts. So, okay, we're getting through there. There's part 2 done with the question. Just got room to finish off part 3 as well. And this was the reason I wrote these down, because I thought I was going to need Suvat equations. By considering the values of time, distance and speed, show that an object starting from rest, in other words, all this information that we wrote down, show it can't be moving with constant acceleration. I'll just change colour to black for this. If it's moving with constant acceleration, the Suvat equations would apply. So I'll just say consider SUVAT equations. Let's see what happens if we put some figures into them. Using v squared equals u squared plus 2is, we would get 1.5 squared equals 0 squared plus 2 times a times 3. And that would give us a equals, the acceleration was 0.375. Using, on the other hand, what should we use? V equals u plus at. Running out of room a bit here, but hopefully using v equals u plus at, that would give us 1.5 equals a times 5. So a would be 0.3. Two different values of the acceleration. They're not consistent with each other. So it doesn't fit with the Suvat equations. I just write, if I can squeeze it in here, if my pen works in this bottom corner of this board, inconsistent is what I'm trying to write, but there's a lag on it. Inconsistent. Oh, that'll do. I know it's not lovely, but right. So this information, the figures, don't fit with the Suvat equations. They're inconsistent. So that's okay for part 3. Let's just do the mark allocation for these parts 2 and part 3 then, shall we? We've got an M1A1 for the work done, and similarly an M1A1 for the power. Right. And for this proof that they're inconsistent, we've got an M1A1 as well. So yeah, that's a total of 6 for those 2 parts. Okay. Last bit of the question coming up then. Right. The reason the acceleration is not constant is that the retarding force is not constant. Okay, calculate the total work done by the retarding force S. Well, there's a bit of energy here then. We know the work done by the pushing force. Let's just create an energy equation, then we can fill the numbers in. The work done by the pushing force will equal the gain in kinetic energy if there wasn't any resistances, that would be it. So in this case, the work done by the pushing force, where's all that work gone? Well, it's increased the kinetic energy, and it's also gone into work done against S, work done against S, this force we don't know, and it's also gone into work done against friction. Let's call that FR. Okay, let's put the values in then. The work done by the pushing force we know from the previous part is 172. Gain in kinetic energy is a half times mm is 16 times 1.5 squared. That's the final velocity. Plus work done against S, so let's call that WD. And the work done against friction is mu r times 3. And mu is 0.25. 0.25 times r times 3. So that's our equation. But just pause for a minute. R isn't the same as it was earlier on. R has changed because we've got... You might like to go back and look at the diagram. R is now 70 sine 35 plus 16g when you resolve vertically, and that works out to be 197 newtons. So our equation now becomes 172 172 minus 147.7 minus 18 equals work done, finally giving us that the work done by S, where's that? What's happening with my pen there? Work done is equal to then 6.3 joules. Right. Just so I just put a bracket around that so it doesn't look as if it's part of that other line. That's the final part of this question, and the marks for that bit were a total of 7 marks. So there was an M1, there was 2 method marks and an accuracy mark for creating an energy equation, an energy balance equation. And then there was another M1 A1 for finding the reaction in this case where the force is now 70, and another 2 marks, 2, 3, 4, 5, another 2 accuracy marks for getting the correct answer. Yeah. Okay, thank you for listening. That was June 2010 question 4, and there's some information on the Further Maths Support Programme.